the new normal. Thank you very much for the invitation. The purpose of the presentation is to share experiences that we have made in Cape Town regarding microplastics research. Ali said we've been doing it for a couple of years. I've been using that term new in the field of microplastics, but I'm not sure for how much longer we can use that term of new in the field. And the purpose of today is to share, and in all contexts. I'm especially keen to have feedback in terms of the good and not so good, where can we improve, but I think above everything to foster collaboration. Just to give context, I think we're all familiar with what's happening globally, but there may be some who's new, and I just thought I'd just quickly contextualize where what we're doing fits in. Globally, there's a challenge with litter, plastic production, sorry, better said, and subsequent to that is increased litter, particular plastic litter. Globally, you can see that there's a challenge around the eastern part of the globe, but I think Africa is also, in terms of the red components, which is the proportion of waste, there's higher proportion of waste being produced in Africa than the rest of the world, it's particular first world countries. I think we're familiar with the publication by Jambek et al. 2018. The left-hand diagram illustrates mismanaged plastic per capita. In particular, look at the darker circles, which is the forecast for 2035. But the diagram to the right shows forecast for 2025, and we're not that far away from 2025. And if the yellow circle is bigger than the colorblind green, it's expected that mismanagement of waste will increase. So across Africa, there is an expectation that waste, in particular a large proportion of it being plastic, will be part of mismanaged waste. And we need to know, I think, what the concentrations of these plastics are, and ultimately, more importantly, I think what the effects of these plastics are. In Africa, some plastics research that was done by Kindile and Alimba, 59 publications on plastics. And all I wanted to indicate here that it was mainly focused on plastics in fish. Proportionally across the continent, South Africa made a huge contribution together with North Africa, West Africa. But interestingly, marine is 52%, estuarine 19%. So together, coastal plastic research makes up about 70%, of which freshwater only about 30%. So there's a mismatch between coastal and freshwater research on plastics. For microplastics, Alimi et al. Reviewed outputs from 56 articles. There were 71 studies because some of the papers had multiple mediums which they studied. And it is interestingly that only 13 out of 54 countries have reported research on microplastics. I think it has increased in a long while. I've seen a couple of papers from Morocco, but there's a mismatch in terms of who does what and where. Darker blue is more publications. So Africa is, I think, in producing more research output on microplastics. I think a large contribution to this was the first work done by Nell et al. A couple of years ago. But there is an increase in the scope of microplastic research and the medium in which the research is taking place. And so I think the gray areas indicates a need for research in microplastics across the continent. In terms of what we're doing at CPUT, I think it's, so I'm just trying to, in terms of what we're doing, the aim of what we're doing at CPUT is to assess the characteristics and later the effects of microplastics. And we're also interested in the associated contaminants linked with microplastics within the coastal ecosystem. Now, there's a lot of, this diagram is very busy, but it just shows you different kinds of sources, be it secondary, which is the breakdown of plastic particles, or primary sources, which is intended for certain products, where it ends up and how it moves. There's a lot going on, but for us at CPUT, we want to focus on the intertidal the intertidal area, but we are looking at catchment to coast. We're focusing on Cape Town because it's in our area. We have a three-pronged approach in terms of the research plan. The first part of the plan is to do baseline studies, in essence, what is where, focusing on water sediment, and we're focusing on intertidal invertebrates. Then we're starting to look at the uptake of microplastics in intertidal invertebrates, but I'll not be presenting that today. And then ultimately, I think to consider the effects of microplastics, there needs to be some indicator. And we're looking towards developing a biomarker to assess the impact of microplastics in association with contaminants such as metals and organic contaminants. Of late, there's a strong emphasis or move towards quality control in microplastics research. I think it's one of the fundamental aspects that I must admit we did not consider when we started the research. And we're continuously working towards improving quality control in the research that we're doing. So I think there's scope for quality control research within the lab. In terms of the team, the lab is not the space. The lab is the team. And without the team, there would not be a lab. And I'll, on the onset, express sincere thanks and gratitude for all that's involved in the lab, especially Dr. Alatunja Awe, our postdoc. If I drop tomorrow, he's the one that will take over in every aspect of what happens in the lab. And his expertise is in chemistry, and his focus will be on looking at microplastics and the associated contaminants such as metals and organic pollutants. We then have a host of students. And briefly, we have Whitney, who's working on microplastics in the catchment area. She's sampling from streams and a flay. Danelle, who's looking at echinoderms in the thousand from the whole Western Cape. Liam is looking at the different feeding groups within the rocky shore. Rushdie is looking at the effect of stormwater pipes and biodiversity in intertidal and subtidal areas. Alex is looking at comparison between beach litter and microplastics and an impact and a control site. We then also have collaboration within CPT with Professor Opiolo, but this is focusing on freshwater, and her team is Dr. Perel, who is a postdoc working on microplastics in wastewater treatment plant. Asmat is looking at a coastal river, which is Rietvlei, close to Table Bay. Komlan is looking at a catchment river further upstream in the catchment area. And Sichle is looking at wastewater plant and microplastics in the river. We also have current collaborations with Two Oceans Aquarium, and we looking at expanding collaboration a bit further. So the purpose of today's presentation is to share what we're doing. And these, from the onset, there's experts in this room. If we're not doing something right, or you think we can improve, by all means, tell us where we can improve. Please do that. We also may have people who's interested in starting, not sure what to do. The plan is to share what we are currently doing on a very, very, very low budget. And we would like to collaborate. We're open to sharing ideas across the country, and I think for this purpose of this presentation, across Africa. And I think that there's scope for collaboration because we've tried to do things on a low budget. We don't have a lot of money. Having said that, I think firstly, the whole question about doing microplastic research and the effects of plastics. And I'd like to put the point that I think it's okay to use plastics in microplastic research, well, at least for now, because plastic is cheaper to source, to use. And yeah, I'll show you the picture. When we started, we used plastic because that's what we had. You will see that for water sample, we used a plastic bucket. For sediment sampling, we're still using the plastic quadrant and buckets and plastic bags to store our sediment samples, and even to collect our specimens. But with that, we are working towards improving the quality of the research we're doing. We're following the guidelines like the ZAMP 2019, and we as best possible, follow the protocols as per ZAMP. And what I'm going to present subsequent to this is what we're doing in the field, in the lab, our microscopy, our polymer ID, and something about the data analysis, which I think is important when we do and to write up our results. We did not have as extensive quality controls when we started, but we are working to improving that all the time. And it's now what I'm showing is now what we in the future will be doing with research going forward. In terms of water sampling, what I'm going to do is just show you what we do in the field for the different media. We collect samples at about 30 centimeter depth. We don't have a boat. And again, that's one of the things we'd like to collaborate on is open water sampling. So we go knee deep and we sample the surface water, put water into the bucket, top it up with the 20-liter bucket. And then we pour that through a mesh. We used to do one mesh, a 250 micrometer mesh, which we subsequently changed. I've indicated the distance because I'll get to this later on, but I think for microplastics research on its own, I think 5 meters apart is ideal. But I think there's a need to sample litter and microplastics at the same site. If we're sampling litter, I think it should be 25 meters apart because we're sampling litter over a 100-meter stretch. And 25 meters apart would be able to sample microplastics within that same stretch of beach. So we then pour the water through a mesh, but we've subsequently changed it to a 250 and 63 micrometer mesh on site. Previously, we used to take a 20-liter bucket to the lab and then process 5 4-liter replicates through a 20 micrometer mesh. And I'll show you the difference at the end of the presentation. We concentrate everything into a falcon tube, and there you can see Donnell and Rushdie. Well, this is Rushdie, he's the falcon tubes here. And then we store it in the lab until we do the filtration of the microplastics. Because it's in the fridge, it needs to be processed as soon as possible after collection. These are the quality control systems we put in place. And that's the same for all field sampling. We need to pre-clean all containers, be it plastic or we try not to have glass in the field. We thought of doing that, but I think in terms of practicality, walking on rocks and jumping over places, glass may not be as safe as plastic. Some wear lab coats in the field. That may not be practical when you're climbing over rocks. So we've decided to have samples of clothing that everybody on site wears and put that also into a falcon tube. So we have idea of fibers from the participants in the field. We also then have an open container nearby. We stand downwind, and we also use empty containers, whatever we're sampling, as also for as controls. Just interestingly, this is a plastic bucket. This is a metal bucket. We subsequently purchased metal buckets. And after lockdown, we tried to resume activities, and we found that the base of the metal bucket was lined with glue, and that glue was starting to peel. And I think this would be a greater source of contamination than a plastic bucket that did not have that glue at the base of the bucket. So we decide we're still assessing the metal buckets, but just be wary that even it's metal at the base, if maybe it's just a poor quality bucket that we sourced, but the glue was starting to come off from the bucket, which was not good. For sediment, same in terms of the strand line, 5 meters for individual sediment or 25 meters if sampling for beach litter. We use a 25 by 25 centimeter quadrant. We used to have a big quadrant and take random 5 centimeter scoops. But I found that it wasn't random when we were not in the field together, and it was biased. So if you're taking supposed random samples, there's potential for bias if you see a nurdle or piece of plastic somewhere and you want to scoop it. So I decided that we scoop the entire quadrant and put that into a plastic bag and Ziploc bag. Then the samples are stored until we do the extraction and filtration. If again, everything is pre-cleaned, as I mentioned, for the water. For the invertebrates, that's Rushdie looking for some invertebrates. We need to ensure that we have the permission to remove the animals, so a permit is important. Different literature sources indicates different numbers of organisms. I think in terms of practicality, we thought of 30, and students struggled to process all the samples because it was so many. So we've agreed on 20 organisms per site. Please make sure that we have the right tool to remove it. And we recently trying to sample sea anemones. And if you don't have the right tool, it may be difficult. For example, limpets, once you touch them, they clamp down. It's difficult to remove them. There, as far as possible, use metal objects. Again, placed in Ziploc bags. The problem with this method is that all the organisms are pooled. And if you seepage from the animal, you may be losing microplastics. So what we do is, when we defrost it from the Ziploc bag, whatever is defrosted, the water, we filter, and the number of microplastics from that water, we filter for microplastics, and we divide it by the number of animals that was in that bag. Again, the same quality control within conditions within the field. When it comes to the lab, key purpose here for any microplastic lab is a pump. We've learned the hard way. I think we've lost 3 or 4 pumps already. If you don't have a vacuum shield protection for the water overflow, it damages the pump. I'll get that in a few moments. So I think a pump and a Buckner funnel system is the key aspect for microplastics, and that's a minimum that you need. So in our system, we filter using this Buckner funnel system, and we use a mesh, 20 micrometer mesh, which we place on the Buckner funnel system. We filter it, and the mesh we remove and then place into Petri dishes, which we store for later microplastic identification. We're very thankful for the Benguela Current Convention. As of this year, we now have a milli-Q water system. So we're using ultra pure water in everything that we're doing. Previously, we had a reverse osmosis system, which I'll show you the cheap one. So filtration. We just filter it onto 20 micrometer mesh. For the sediment, we do extraction and filtration. Extraction, because the sediment, microplastics is in between the sediment, we need to extract the microplastics from the sediment. And the way we do it is we make up a hypersaline solution, 359 grams per liter. That hypersaline solution is added to the sediment. We stir it, allow the sediment to settle, and the supernatant, which is the top part, we pour over the Buckner funnel system, and we repeat that another 2 times. So again, everything is stored in a 20 micrometer mesh in Petri dishes for microscope work and FTIR work. We also process the sediment for grain size analysis, because I think it's important that we try and assess if there's any influence of sediment size on microplastic size and concentrations. For the biota, we digest the biota. So we put it's a mussel into a jar. We make up a 10% potassium hydroxide solution. We ensure that the soft tissue is covered. It's after we've measured it, the length and weight. Once it's the 10% acid has been, potassium hydroxide been added, we put it in an oven for 24 hours at 50 degrees Celsius. Sometimes it depends on the tissue. We found that some tissue needs more time to digest. So after a while, just give it a stir, and if it's digested, then it's okay. Sometimes you leave it for a long time, but it doesn't digest completely. It's okay. That's what it looks like if it's sometimes digested, but there's still some things on there. But as long as most of the tissue is digested, and then on from this, and this is the 20 micrometer mesh we serve everything onto. And from there, we store it again in Petri dishes for microscope and FTIR processing. So that's the biota, invertebrates that we sample. When we get to so now all the samples has been stored, it's dried out, and now we're ready for the next step, which is the microscope identification. We use Gazump again to classify based on the type, whether it's a fiber, fragment, film, sphere, the colors as per Gazump. And The size is still an issue. We initially thought of filtering through different size meshes, but it take a bit too long. So at the moment, at the base of the microscope, we have graph paper, and we estimate the size of microplastics based on the size categories from 1 millimeter graph paper. So that's how we've categorized the size of microplastics. It's a bit challenging, especially when microplastics such as fibers are twirled and all twirled up. There needs to be an estimate of the complete length of it, not the linear length. Once a student starts or person starts, very, very important for all of us is that another person validates that person's count. And that should be done as early as possible, because if you cannot wait until you've processed all the samples and then somebody checks it and then we realize, but you didn't identify something correctly. So it's a conversation that we have in the lab. I encourage students to validate each other's work, and then I will come in and Dr. Way will come in to randomly check the counts. If it's far out, then it's a longer conversation around what are we classifying the microplastics as. Once we're done with that, it then gets captured into Excel, what we've recorded, based on, again, type, color, and size. In terms of data, we have all our categorical variables stored to the left-hand side of Excel. Because we're using SPSS and we want to work towards R, there's certain formats that the data needs to be in order to do that. So we just give a guideline in terms of, on the left-hand side, the categorical data. And then for this site, we only found filaments, fragments, and spheres. The counts, the color, and the size, these are just in millimeters. What's not on here is the conversion to numbers per unit. And the numbers per unit is, if in the case of mussels, it'll be the number of microplastics total divided by the tissue weight to get the estimate of the microplastics per weight. We also then insert the column, if it's water, the volume sampled, and for the sediment, how much sediment was processed. So we divide the numbers by whatever unit was used for water, sediment, or organisms, which is indicated here. Then we've recently, again, we're thankful for the Benguela Current Convention, support for an FTIR. We've also sourced a microscope. So once the petri dishes have been, or the samples have been identified, we then put that on a microscope. We find a microplastic particle. This is a microscope camera. So it's live, and you can see there's a microscopic particle. There's a nice scale bar. Not for every item, but we take a photo. Once it's been done, then with a tweezer, and you can see there's another magnifying glass here, moves over to the FTIR. It's clamped down, and then we scan it. We've also sourced the East Japan library, because I found that was a problem in terms of the polymer scans for the different polymer types. We're also going to be using the polymer risk index, which is based on the hazard scores by Lithner. But that's work in progress for the students. I'll still need to do that with all of the team. But that's the idea. I think we can do that going forward. So in terms of microplastics, the tight budget, this is where we started. It was a chemistry lab that because of the chemistry department moving to another campus, that's where we started. And that's where we ended pre-COVID. We had a pump, one vacuum pump, and I'm smiling because this was an oil-based pump, and students didn't check the water levels. And the honey jars at the back was when we had to drain the pump because that was mixing with water and oil. Surprisingly, this pump has still survived. Our newer pumps, which is this one here, some of them did not survive. But that's one of the challenges if you do buy a pump, an oil-based pump. That's the Buckner funnel system. We had an oven, and everything else, the glassware, the petri dishes, part of it was from my previous research, but to source those are not that much. We borrowed where we could. This is a sediment shaker, which we borrowed from the department. I think it's been returned of late. I also said we made up our own water. This was the simple water purification system to make up our own reverse osmosis water. The problem with the system was that it was very slow. and it often became clogged because we were using water from the tap. We filtered everything. Before we got the molecular water, we filtered everything through 10 micrometer mesh. I even put mesh on the tip of the taps, and we could slowly pour out water if we were rinsing things. All it needs is the mesh, but you could filter it through 10 micrometers, putting the mesh on here and securing it with an elastic band. Not ideal, but that's what we did when we started. Then COVID happened, and subsequent to that, we've now had to put safety measures in place in terms of sanitization. We've inserted shelving to separate the workspaces, and as a result, each workbench, it becomes a separate unit. It has its own glassware, its own pump, its own scale. There's no sharing of anything between workbenches. And yeah, each unit has its own equipment and consumables. We've then had to source a new oven. So we now have 2 ovens, and then, as I said, we now only use molecular water in our lab. We're thankful for that. In terms of the way forward, we want to look at the effects of microplastics, and Dr. Aware is focusing on metals. We are having a challenge with COVID and having access to labs to process metals, but we hope that will be resolved. In South Africa now, all adults can go for their jabs, and we're hoping that in the coming months, we will go to some kind of new normality, and as of next year, I think things will improve. Ultimately, we want to walk towards a biomarker for microplastics, and the approach on campus, we have an oxidative stress lab, and we want to use antioxidants as potential biomarkers. But that will be looking at metals and organics together with microplastics as we develop this biomarker. I think there's a need for more baseline data everywhere, because I tried to use the pollution load index for the research article, but part of that requires the contamination factor, and the contamination factor requires a baseline background concentration, which we don't have. So I think there needs to be an intensive move towards baseline studies everywhere. I think there's also a conversation that needs to be had in terms of whether, when we are busy with microplastic research, should we not also be collecting samples for litter, even if we can just identify the major types. This is researched by Alex. We sampled an impact site at Woodbridge Island, which was Milnerton, close to a downstream of a river, into Table Bay. And there, it's in a nature reserve, far removed from human and other activity. I want to say there's potentially a negative correlation between microplastics and litter, but I don't think there's enough data points to say that yet, at least for the impact site, which is the dark green. For the blue, I think it shows positive correlation, but there's something to be potentially said in terms of the relation between litter and microplastics. I also mentioned earlier on about the standing operating procedures. Globally, for water, and here I'm referring to water samples collected by manta nets, maybe less so in streams, but wherever manta nets or moving nets are used, generally the mesh is about 250 micrometers. And as an experiment, we sampled both at 250 and 20 micrometers, and we did this in 2019 and 2020. I'd like to point out the scale on the y-axis is different for the 2 years because it was much more in 2020. But in essence, by just comparing between the 250, which is the lighter gray, and the 20 micrometer mesh, we can see that for almost all sites, if not all of them, there was more microplastic collected when we served on the 20 micrometer mesh. So I think there's a conversation to be had in terms of SOPs, especially when it gets to water. So in conclusion, I think it's a continuous discussion in terms of to improve what we're doing, but I think there needs to be minimum standards. I don't think we can compete in terms of minimum standards with first world countries. I think for Africa, it needs to be sensitive in terms of localized conditions that is practical and cost effective. I think that's an important point. I also then think there needs to be a litter and microplastics working group where discussions can be had, where we do establish these SOPs. And I think for standing operating procedures, I don't think there's anything wrong with using citizen science methods For microplastics, for example, there's the big microplastic survey that was developed by the University of Portsmouth. It uses household sieves, for example, to sieve beach sediment. But I think there's an opportunity, there should be an opportunity for more baseline studies, even if we use methods that may not be as technical. Whatever we're doing, I think it needs to inform policy decisions. Globally, there's an increase in plastic pollution, and the effects of it we don't know, really. But I think as we move to that, there could be an intensive effort in terms of baseline monitoring, just knowing what is where for future studies where effects can then be later understood. I'd like to thank everyone involved, especially the Cape Peninsula Technology, CPT, for the space provided, some of the funding for some previous studies, the Benguela Current Convention, and the Department of Forestry, Fishery and Environment for support for the Milieu water system and the FDIR, our partners in Two Oceans Aquarium, City of Cape Town, Cape Nature, and then last but no way the least, the NRF, the National Research Foundation, for the funding that they provided for the microplastic research, and then ultimately the team within CPT. Without the team, nothing could be possible. I sincerely thank Dr. Ware, the postgraduate students, and even the undergrad students who assisted with some of the field sampling. I thank you. Yeah, it's now 25 to. Thank you, everyone. And if you do have any questions, please feel free to ask them.
Thank you very much, Conrad. That was really great overview, and it's nice to see how your lab has changed and adapted with COVID and with everything. We have already got a question that was placed in the chat, which I think you have kind of answered, but maybe you want to talk more about it while we carry on, and then we also have a hand. The question was by Neela Vanan, who spoke mainly about, and I think this was before you spoke about the different mesh sizes, but they wanted to know what the standard sieve size was for sediment in plastic pollution, and basically is there an actual standard mesh size? And I think you did mention it with about the 250 and 20, but whether that is actually a standard globally, I think it's about 300, I'm not sure.
Thank you, Ollie. It's actually a very interesting point. I didn't mention this. Globally, actually, I think it depends on the medium, but filter paper is actually used, and it could go down to micrometers. And I tried that initially, but especially with biological material, I think the first time I did it, I used 10 filter papers just to filter one organism. And then already I realized that I'm not sure if it's just me, but I don't think that fine filter paper will work, especially with biological material, which sometimes everything does not digest. So I think we intentionally moved the challenge with this, the mesh is nylon. But I think if we have controls in place, 20 micrometers is practical, and it is cheaper than buying filter paper. Filter paper can be very expensive, and it only can be used once. With the mesh, we can clean it and reuse it. And that's why we cut it up into these squares and put it on. When we are done, the idea is to recycle, to clean it, and then reuse it. With filter paper, that's not possible. So as a minimum, I think it depends on the purpose of the research question. If it's for monitoring, I think 20 micrometers is fine. But if you want to focus on smaller microplastics, especially with micro FDIR, which we're not doing, we don't have that micro FDIR, so we cannot look at microplastics that small. So I think for what we are doing, I think 20 micrometers, the mesh is ideal.
I think you've actually answered another question that came up in the Q&A by Francis, who asked what the 20 micron sieve or mesh was made of, and yeah, so it's made of nylon.
It's not. We would love to get a metal mesh, but again, to recycle, the problem we have is, I think it's here. You need, because we had to wait for the FDIR. And I learned this the hard way. The first group of students, once they were done with the microscope work, they discarded their samples because we didn't have enough mesh at the time. But after they had discarded it, I then wondered about the numbers, but then I couldn't go back to anything because the samples were all gone. So the problem with this mesh system is that you need to have a lot of petri dishes and lots of mesh. And my suggestion then is only after the paper's been published, if that's the purpose, only then discard the samples. Mm-hmm. Because I realized we sometimes need to go back to validate, to check something, even during the publication stage.
I actually, just as this is a knowledge sharing opportunity for our team in the University of Birmingham, we use nylon as well. And we did actually start using stainless steel mesh. And I found that the stainless steel mesh wasn't actually that easy to clean, and we had more contamination. And this is one of the points that you mentioned was, you know, non-plastic alternatives may not always be the perfect alternative, and you still have to see whether there is contamination, because we found that the nylon meshes that we use are a lot easier to clean, and then there's less cross-contamination between our samples than it was for the stainless steel. So it's a very good point.
Okay.
We have another question in the Q&A by Yati. When sampling organisms, such as mussels and cockles, for microplastic analysis, is it important to consider age and size of organism?
I think it's important for consistency of size, because it's not here, but we did a research on microplastics in mussels from retailers, and we actually found an inverse relationship between microplastic in the mussels and size. So I think if you, within the adults, keep the size category as similar as possible. But I think it depends on the research question. If you want to compare between, you know, juveniles and adults, that's a different research question. But I think try and keep the size as similar as possible. It may not always be possible. If you're in the field and you find that they vary quite a lot, I'd rather have a wider size range than have nothing at all. But in this, I'm not sure if you can see it now, in terms of the 20, try and keep the size range with as close to limits, extremes as possible, because that will affect the variances of your data, and you don't want to have high variances from your replicates.
We have another question from, again, I do apologize if you do want to put your hands up and ask these questions, more than welcome. So I'm sorry if I get names wrong, but Hussan said, great talk, Conrad. Will you consider sampling sediment using core sampling techniques, polycarbonate tubes, to study vertical variation?
It's a very interesting question and point. Peter Ryan just published a paper on beach sediment, and he used cores. He used 12 centimeter cores twice. So he sampled the top 12 centimeters and immediately beneath it another 12. And he actually found more microplastics deeper down, mainly fibers. So again, I think it depends on the purpose of the study. I do think, though, it's a bit specialized. So if it's for a research question, I think it can be done. But for monitoring, I think we need to keep it as simple as possible, because I think we should move towards similar methods. The volume of the cores and the depth differs between surface sampling, and I think you're sampling less of a surface area with cores as if you would with a quadrant. So I think it depends on the research question. If the purpose is to assess depth of the microplastics, then I think cores will do. It's good. But if it's to get a baseline and based across different sites, I think scooping the surface and putting it into a Ziploc bag would be simpler.
I don't see any more questions. If there are any questions, please, and you're welcome to raise your hand. And I have looked through the chat and can't see anything. But while you're thinking of questions to ask Conrad, I thought maybe if you don't mind, I'm going to ask a question. And it's a bit of a difficult question, and it's a question that I know some attendees might have heard me talk about before, and it's something that I'm battling with at the moment. And this is for everyone in the network. You know, we know that we're having in Africa, we've got limited funds when it comes to the infrastructure needed for microplastic analysis. And we also know that a lot of these microplastics are coming from solid waste, poor solid waste management. So do you think we're wasting our time looking at microplastics and we should just be focusing all our attention on solid waste management and litter and large litter and things like that, which are easier to monitor, because you are talking about monitoring on this point of view? I know it's quite an open-ended question, but it's really just something that I'm battling with at the moment as well.
I think that's why I made the point, especially this one, in terms of baseline, do we need to sample litter as well? I think the two goes hand in hand, and the student Alex, he's sampling both litter and microplastics. The secondary, the degradation of plastics, and the source of secondary microplastics comes from the litter. So I think it's important to I don't want to say look at both fronts, but we're looking at microplastics which could be further down the line from the current litter challenges we have. So, but if we have an understanding of both now, I think it could influence, some say, in terms of policy decision, because if there's a lot of microplastics of the same type as the litter, then we can say, if you have this litter, we can expect microplastics down the line to be this, if we're sampling both at the same time. Mm. So I don't think we should say, yeah, there's not a lot of microplastics, when I could argue we don't know what is there because we have not sampled for microplastics all over. So it could be there. It's just that we're not recording it. And that's why I make the point, let's sample everywhere now. And even if we're using citizen science approaches, it's okay as long as it's consistent. That will give us an idea of the microplastics. But in terms of the relation between microplastics and litter, I have not seen that many research output. And it's becoming more and more in documentation from organizations saying we need to know what litter, and now I'm seeing microplastics included. So I think we need to do both. But we must not complicate things. I really think we must keep it simple. So for the litter, Wyomsa, for example, they've developed a protocol for the Wyomsa region. Why not just adopt that for the entire African continent? The guidelines is there, the appendices is there, the data sheets is there. There are some challenges, I think, with that, but I think it's something to work from. The microplastics, there's the big microplastic survey method. Again, it's taking 2 buckets, a serve from home, and you pour through the one, and then you record what's there. It's better than nothing. But because we don't know what is where, I think it's difficult to influence not policies, but in terms of the research and ultimately the impacts.
I think you also make a very good point about this baseline data, because if we tackled large litter and we saw a decrease in large litter across Africa, we would think that we've done our job and everything's fine, but we might still be seeing increases in microplastics for years to come because of the litter that's already in the environment. So we really need that baseline data. I see, Hendrik, you've got your hand up. I'm going to allow you to talk. You should be able to join us now. Asked to unmute. You are part of the panel now, so you should be able to unmute. Ah, there we go. We can't hear you yet. Hello? It says you're unmuted.
Can you hear me now?
Ah, there we go. We can hear you now.
Sorry, there's so many buttons on my headphones and things like that.
No
Hello,
worries.
Holly, Conrad, and the others. Conrad, you spoke about the background. I was curious how you handle the background. Do you subtract total numbers from total numbers, or do you subtract, say, fibers from fibers, etc.? How do you handle that? That's one part of the question. The others, do you use field blanks? Thanks.
In terms of background, are you speaking about the controls that we use?
Yes, you know, the lab controls, if you pick up, say, a lot of fibers, do you subtract it only the fibers, or do you subtract total numbers from total numbers, or how do you handle that?
It's a very interesting one. We would just subtract it from the fibers, because the fibers that would be found in the petri, well, the contamination is mainly fibers. I don't recall seeing a fragment from the airborne contamination, so it would be fibers. So we would subtract it from the fibers that we have in the samples. Yeah, so the fibers would be the background or the controls. If it's fiber, we would subtract it from the fibers and not necessarily from all the microplastic types. In terms of field blanks, we take empty containers. So if it's the Falcon tube, we will take, I can just see now. In terms of, yeah, if it's a Falcon tube, we should take empty Falcon tubes, and then we would process the Falcon tubes without any field water in it. So to see if there's any contamination from the Falcon tube itself. So that's the one control. In terms of the negative controls from the field, we did not do that initially, but we would now put not a bucket, but a container next to where they are, open it when they're there, and then close it, and in the field, process that container with molecular water to see if there's any airborne contamination that ended up in that container. So that's how and we would do that in the field for the duration that they were in the field. And then in the lab, in the lab, on the one hand, just quickly see here, when we're in the lab itself, if a person is standing here, they would have an empty petri dish next to them, and it'll be open for the time that they're working here. When they're busy with microscope work, they would put the empty petri dish next to where they are for the duration that they're at the workstation, and then see what any contamination from airborne when they're busy with the microscope work. And whatever fibers is in there, we would then subtract from the final results, fibers only. I don't know if that answers your question, Prof.
Yes, thank you, Conrad.
Okay.
Thank you very much. We've also got one more question from Bayati in the Q&A, but it's more, I think, an invitation if Conrad, if you want to get hold of each other, if it's possible to work together on some FTIR analyses and things like that. I think Bayati works in Lake Victoria, but please correct me if I'm wrong, but we heard about his work in James Wikivia's talk last week. So I think, yeah, I don't know if you want to, yeah, you're welcome to comment on that, and then I will just wrap up.
Are you referring to the one about sending a few samples at your lab for FTIR? Yes, please. That's what it's there for. We're really open to collaborate. This is my email address, sparksy@cpt.ac.za. We would happily assist where we can. I think it depends on the number of samples. The university opened less than a month ago, and all of our students need to process their samples for FTIR analysis, and that's beside Dr. Wen I in our own research. So if it's a couple of samples, I'll just bump the queue from the students and process a few samples, not a problem. But I think there's potential for further collaboration in terms of polymer and education. So by all means, yeah, we really want to open discussion with colleagues all across Africa for collaboration. No problem. Just send me an email. We can chat about it. No problem.
Awesome. Well, thank you again so much for giving us an insight into your lab. And I think these kind of talks are really useful for not only people who are starting up labs, but also for us who have been working in the field. And trust me, we are all there. I mean, I've learned a couple of things, and the fact that you can put something over your tap, I didn't even think about that. It's such a nice low cost way of making sure that because tap water is contaminated in different labs differently. So that's really, really such a useful tool and technique. Yeah, so this has been live streamed, and you're welcome to check it out if you missed any of it, or share it with anyone. And if you do have, I know that a lot of you have been getting the emails about opportunities to collaborate. If you are looking for partners around Africa, or you have a proposal and you need partners in different countries, or you're looking to do a multi-country study and you're looking for people to work in different countries, please contact us. That's what we're here for. We can send it out to our network and collate a mailing list for you, or contact list for you to then take further, and hopefully that will do exactly what Conrad is saying, is reach out to different groups and really create this African-wide expert group that can then look at monitoring and things like that. So thank you very much again, and thank you everyone, and we'll see you next month.
Thank you very much, Holly, for arranging this. We'll look forward to the next one. Thank you.
Bye.
Bye-bye.